Hello everyone. In this video, we will cover fractional ages. Usually the live table only lists entries for integral ages. X is an integer. So that it is not sufficient to compute probability involving non-integral ages or non-integral durations or both. For example, 11.5 P60, we have non-integral duration. 10 P35.2 non-integral ages or both 4.8 Q 80.5. To compute these probabilities, we need additional assumption called the fractional ages assumptions. We require assumptions about the distribution of the future lifetime random variable between integral ages. And in this series, we cover two fractional ages assumptions. The first one, uniform distribution of death, in short, UDD. The second one, constant force of mortality. In this and the next two videos, we focus on UDD, and then the following three videos, we focus on constant force of mortality. What is the UDD assumptions? Suppose X is an integer. So at age X, we have Lx, and at age X plus 1, the expected number of survivors is Lx plus 1. We assume a linear functions linking up the Lx and Lx plus 1 at age X and X plus 1 respectively. And the slope is minus dx, the expected number of deaths between age X and age X plus 1. For S is between 0 and 1, so that is any age between age X and age X plus 1. We simply use interpolation to get Lx plus S. And this is the interpolation formula to get the value for Lx plus S, which is 1 minus S times Lx plus S times Lx plus 1. And then we can rearrange it so that we have Lx minus S times Lx minus Lx plus 1. And the last term is simply dx. And we have this expression. Divide both sides by Lx. Then Lx plus S over Lx is simply SPX, which equals 1 minus S times dx over Lx is Qx. And this becomes SPX equals 1 minus S times Qx. And then SQX, which is 1 minus SPX, we have S times Qx. And these two, SPX and SQX, are the key formulas under the UDD assumptions in evaluating the Lx or the probabilities involving non-integral ages. How about the force of mortality between integral ages under the UDD assumption? All right, we take the derivative of SQX with respect to S. So this is the derivative of S times Qx ds, and this simply is Qx. And we have a density function. The density function is simply dtqx dt, and this equals tpx times mu x plus t. And on the left-hand side here, we have this density function, and this is spx times mu x plus s, and this equals qx. And therefore, we have the density function, which is a constant between integral ages. And this constant is Qx. Solving for mu x plus s. And then SPX is simply this expression, 1 minus S times Qx. And we get a formula for the force of mortality, mu x plus s, where s is between 0 and 1. So this is the force of mortality between hx and hx plus 1. All right, so let's work with the two key formulas, SPX and SQX, with an example. Given that Q80 is 0.04 and Q81 is 0.05, calculate these quantities under UDD assumption. All right, we have the key formulas. SPX equals 1 minus S times QX, and SQX is S times QX. The first quantity, 0.4 Q80, that is an individual currently at age 80, will die before reaching age 80.4. And here we have S equals 0.4, and then X is 80. This is 0.4 times Q80. Q80 is 0.04. We get 0.016. The second quantity, 0.65 P81, an individual currently at age 81, can survive beyond age 81.65. S is 0.65, which is between 0 and 1. Apply the formula, 1 minus S times QX. And S is 0.65. The second term is 0.65 times Q81. Q81 is 0.05. From that, we get the probability 0.9675. The last quantity, 0.4 bar Q80, which is 0.4 P80 minus 1.4 P80. The first term, 0.4 P80, remains unchanged because S is 0.4. We can apply this formula to get 0.4 P80. And then the second quantity, 1.4 P80. And now we have S equals 1.4, which is greater than 1. We cannot directly apply this formula. Instead, 1.4 P80 can be factored as P80 times 0.4 P81. And now this expression, we can use the formula SPX for computation. All right, so 0.4 P80 is 1 minus 0.4 Q80, and then minus P80 0.04 times 0.4 P81, which is 1 minus 0.4 times Q81. Substitute Q80 and Q81. And then we get the answer 0.0432. And the individual currently at age 80 survive beyond age 80.4, but die before reaching age 81.4. All right, so this is the calculation involving non-integral ages under UDD assumption. All right, so let's take a look at the difference between UDD assumption between integral ages and the De Morvis mortality law. For UDD assumption, at integral ages, we assume a linear function. Between age x and x plus 1, the function has a slope minus dx. And then the slope between age x plus 1 and x plus 2, the slope is minus dx plus 1. The slopes are different for different integral ages. And for the De Morvis mortality law, we also have something related to the uniform distribution. We have the survival distribution. All right, under the De Morvis law, we still have a straight line linking two integral ages. The slopes are respectively minus dx plus 1, and minus dx plus 2. However, these slopes are all having the same value. Here I call this minus D. All right, so this is the difference between the UDD assumption between integral ages and the De Moivre's mortality law. All right, so far we have done with calculating the probability with non-integral age or non-integral duration, where x is an integer and s is between 0 and 1, and we get these formulas. Altogether 5. But SPX and SQX are the two key formulas in computation. And then in the next video, we will compute SPX plus T or SQX plus T. And here, X is an integer, and S plus T is between 0 and 1, as well as the last case, T plus SPX and T plus SQX. Here, X and T are integers, and S is between 0 and 1. All right, that's it for today's video. See you in the next video.